Atoms are so small, it's impossible to place a single atom on a balance scale to find its mass. And any sample large enough to mass on a scale contains billions of atoms, far too many to count. So, how do we find the mass of a single atom? Maybe there's a trick we can use. We need a kind of universal container that always holds the same number of atoms, no matter what kind they are. Let's take two of these universal containers, each containing a different kind of atom. We can easily compare the mass of the two container loads. This ratio describes the relative mass of two single atoms. It's a way of exploring the mass of single atoms by examining large numbers of atoms. If a universal container exists, what might it look like? Let's choose any two containers which are exactly the same size and shape. Let's fill them with two different kinds of atoms. One with lead and the other with sulfur. Do these two containers hold the same number of atoms? Possibly. But suppose that heavier atoms are larger atoms, and that's a reasonable assumption. It's also reasonable to assume atoms are like marbles and packed together so that they're very close or touch each other. But it takes fewer large marbles to fill a jar than small ones. If atoms behave the same way, their size will determine how many atoms will fit in a container. If we can somehow prove all atoms are the same size, then the two containers will hold the same number of atoms, and we will have found our universal container. But nobody's been able to prove atoms are all the same size, so we need a different approach. Suppose marbles in a jar don't touch, but somehow float some distance from each other. Their size might no longer determine how many fit in a container. There are substances which behave as if their basic particles don't touch. In fact, all substance is in the form of a gas. We can take a known mass of gas in a known volume. Without adding or subtracting gas, it's possible to shrink the gas into a smaller volume. And it's also possible to expand it to occupy a larger volume. This suggests that the particles of gas are somehow floating some distance apart from each other. It's this empty space between the particles which shrinks or expands as the volume of gas changes. How many gas particles fit in a container? If particle size is not as important as the space between them, perhaps under some conditions, a container of gas might hold the same number of particles. It therefore doesn't matter whether the particles are heavier and larger or lighter and smaller. We might have a kind of universal gas particle container if we could control the conditions that change the space between the particles. To explore these conditions, let's compare a volume of gas particles to a concert hall full of people. It's never so full that people are packed in like sardines. They sit instead in seats with spaces between them. Imagine a well-designed seat, which can hold the largest person or the smallest. How many people does the hall contain? Well, that'll depend on the number of seats. One condition that will influence the number of seats is the overall size of the hall, its volume. The number of seats will also depend on the space left between them. A condition that affects this space is pressure, caused by the push of elbows on either side. Another condition is temperature. People must be close enough to be cozy, but not too close, or they'll overheat. So, the spacing between the seats is no accident. It's carefully adjusted to take into account temperature and pressure. Temperature and pressure, together with volume, fix the total number of seats in the hall. Once designed, the hall will always hold the same number of people, no matter how small or how large. Now imagine that a volume of gas behaves like our concert hall. In a particular volume, at a particular temperature, under a particular pressure, there will always be a fixed number of seats or positions available for the gas particles. No matter how small they are or how large. With this in mind, we can use these three factors, temperature, pressure, and volume, to describe the conditions for a universal gas particle container. This is how it works. If 1 liter of hydrogen at a fixed temperature and pressure contains a fixed number of hydrogen particles, then 1 liter of oxygen at the same temperature and pressure will contain the same number of oxygen particles. We can easily compare the mass of 2 volumes of gas and so also compare the relative mass of 2 single basic particles of gas if our idea about the universal container is correct. But hold on a minute here. Have we any right to assume these particles are the smallest indivisible particles, namely atoms? We can certainly hope they're atoms, but we can't automatically assume it. So, for the moment, let's put a bag around one of the particles and remind ourselves that so far we have proposed not a universal container for comparing atoms, but a universal container for comparing gas particles. Since we started out to look for a way of working with single atoms, our search is not yet complete. What we need now is some way of opening up these particle bags and finding out if the particles are really atoms.